Alright, so let's continue the stuff from yesterday. So let's try to do some more image stenography. So I did some refactoring since yesterday and figured out why it wasn't working on this test bin file. Apparently I'm stupid, and let me just find where that thing was. I guess, well, it should be in stack.c, or maybe I was doing some kind of malloc, right? So maybe it's a realloc, right? So I think I was using calloc, calloc, because I said that it initializes everything with 0, but I wasn't using it correctly because you're supposed to pass in the amount of bytes, or I guess the size you want and the size of the element. So that was my mistake here with calloc. I was passing 0 to it for some reason. I don't know why. That's why I was getting that error message, and I said it's the first time I saw it. I don't know why I was being dumb like that, but I guess now I refactored it to use malloc. But yeah, that's like whatever. Hello. So yeah, I guess that was the problem. But I did some refactoring since the last time. Just moved a few files around. So we have this stack.h, which I guess it's just just the name, but it's basically what it's doing is inserting this payload into these bytes. And for yesterday we looked at LSB method, so we tried to hide this payload in the data, in our data, using the least significant bit. And we also added this at the end we added this compression, which what it does is for a compression of 1, it just uses the LSB, but if you increase the compression, it uses more and more bits at the end of the image. And I guess what we saw was that the image looked kind of decent even when you used 4 bits from one RGB byte. So that was kind of interesting. So if we do I have a makefile? Yeah, I have a makefile. That's nice. So if we do something like this, where we try to hide in our Lena image, we call it Lena out, and we hide this test.bin file with a compression of 4, it kind of looks similar. So if we take a look at lena.out, it has some, I mean, it's, for me, it's kind of, I can notice it, but probably on the video it's unnoticeable because of the compression. But there is a bit of a difference between them, but I wouldn't say, if you don't know about it, you wouldn't see it, to be honest. So yeah, that's kind of cool. And then we can actually show that, but here is gonna be a bunch of bytes, right? So we managed to hide a total of almost 400,000 bytes. So that's like what? If we divide this thing by 1024, it's almost 400 kilobytes. So that's, I mean, quite nice. We can hide quite a lot of data inside of this image. So that's quite impressive. But obviously we can do stuff like, let's say we remove everything and we say hello from file, right? And then if we try to hide it, let's say only one, like a compression of 1, so it's using only 1 bit, it's gonna say the message was successfully hidden, and when we decode it, it's actually gonna show us the message, right? So it's kind of cool. It's putting the data inside of this image, but you don't have to think about it as using the like hiding the message inside of the image. We are just hiding it inside of some bytes. So it's kind of like a function that takes some bytes, takes some other array of bytes, and it mushes them together. So that's kind of what it does. And today we are going to try to implement the same thing, but with FFT, because I'm curious if it's going to be more efficient. Like if we were able to hide 400k like kilobytes. Maybe we can hide more with the FFT, but that's something we are gonna see. So let's create this file back, test.bin. Let me just try to, okay, so what if we use a compression of 8? Like that's a good point, right? What would happen? So obviously it's gonna work, but if you think about it, 1 byte has 8 bits. So that means we are using all the 8 bits to store our information. So question is, how will the image look like? How will the output image look like? Well, if we look at it, it's complete like noise, right? Because we modified all the pixels from the image, so it's completely different. Obviously, you can still get the information back, right? So it's still there, but we overwrote all the bytes. So right, because we use the compression of 8. So I'd say maybe the base compression, like probably 4 or 2, it's still good enough. And I decided to keep the compression rate, so you have to use powers of 2. That's kind of a bit like easier to implement if they are just powers of 2. So yeah. Oh, that's cool. The which compiler, the Kruf one or the cool compiler? Curious. So we have this kind of stuff from yesterday, right? So it was kind of nice. And my plan for today, as I said, would be to implement FFT. So here I was looking into the algorithm itself. I would say it's not that bad. Like we can try to implement this one first, which is like the formula. I honestly I have no idea what like what the intuition behind this thing is. I just know that FFT is used to take something like a sequence and look at the frequencies in that sequence. And the thing about FFT is that it has an inverse function. So if you have the frequencies, you can get back the data. So if you think about it, what we can do is to take the bytes from the image, apply FFT on those bytes, we get some frequencies, whatever. We are gonna hide our data in those frequencies somehow. We don't know yet how to do that, but we'll try to figure that one out. And then we take the modified frequencies, we inverse transform those things into bytes again, and hopefully the bytes will look similar to the image, so we'll get kind of the same thing back. So that's what I would hope to see here. Right. And I mean, maybe the some like if you know some math, maybe you notice that this is the like e to the power of negative I times pi, which is, I think it's -1 or something. So it's like this kind of thing. And from what I remember from like the math courses from uni, I wasn't really paying attention. It was like way too complicated, to be honest. It was like insane. But what I remember is that this thing is kind of like sine and cosine or something. So I'm pretty sure that FFT converts a signal into its like into multiple sine waves, and those sine waves like build that signal somehow. So that's kind of the idea, but I really don't know. But we'll try to look at this thing as a programmer, so we're just gonna implement the code for it. Okay, so let's do fft.h. I guess if not defined fft.h, we define fft.h and then we end if. Okay, so let's say that this one is I don't know, naive implementation, because As you might guess, it's O(n) squared, but somehow on Wikipedia it says that it's possible to get it in n log n. We'll see if we can actually implement it. I think the implementation that's more optimized uses divided impera, so it's like computing half of the thing, so it gets log n instead of n. Yeah, whatever. But let's call this one like FFT simple or something. So I guess how this thing is gonna work is, still think I want to return some kind of result, but I'm not sure yet. So FFT simple, this one. Oh, and the cool part about it, it's using complex numbers. That's kind of sucks, but luckily C has a library for complex numbers, and it's in stdlib. So well, I guess I don't know if it's in stdlib, but it's no, is it stdlib or is it like just C compiler itself? Anyway, so we have this thing, so we can say something like double complex, or is it complex double? So this is going to be our input, x, right? We also want the length. I'm not going to use dynamic arrays for this one. I'm just going to make them pointers. Like, we could use dynamic arrays, but I feel like it's going to be easier to have just pointers and lengths. So let's say size t, or maybe just unsigned long. I think it's called n in here. So let's call it n, just to keep the formulas the same. And then we are gonna have the output. Honestly, I'm gonna call it x out. I guess it was the other way around. So double complex, right? Or it's interesting. Maybe whatever. I know that I was implementing the C code, trying to see if it works to have complex, and it was working. So maybe it's just the header, which kind of sucks, but whatever. Let's write also the C file, because we are gonna need it. So include fft.h, and because I'm using Clang as the LSP, and that's made for C++, so maybe that's kind of the annoying one. In like the C file it works. I don't know how you can tell Clang to look at files as C files, but whatever. Anyway, so we have this FFT simple function, whatever. So what we want to do now is to compute this this term, right? So it shouldn't be that hard to do it. So we are gonna start maybe with a for loop for unsigned. Maybe let's use size t for size t. Pretty sure that's something from C++, but whatever. So size ti is equal to 0. I guess here it's using k. So let's also use k. K is less than n, k plus plus. Okay, so yeah, we are just using. I guess k is, yeah, sure, fair enough. K is used for this thing. That's good enough. Okay, so at this point, we want to initialize x out, probably. Maybe say something like x out is 0.0. And we can also use something like times capital I. Capital I is like 0 plus I. or I guess it's just I. I think it's possible to use, if you postfix a number with lowercase I, it makes it like imaginary, which is kind of cool, but let's just write it like this. Okay, so we just initialized k, now we have to do the sum. So let's do a for loop, and here you can see why it's O of n squared. We have two for loops over n, so that's kind of the point. And with the more optimized method, you would get like log n instead of n, so that's kind of the idea here. So yeah. Okay, so let's try to do the exponent first. So maybe complex double exponent. This guy is gonna be exactly this multiplication from here. So okay, so it's minus I. Let's do I times 2 times I think if we include method h, I'm pretty sure it's mpi. I don't know why it's I think it's math underscore pi, right? So that's the reason for the m prefix. Okay, then we have k. Interesting, we have k multiplied by m and divided by n. So I mean, it's just copy pasting from Wikipedia, but we get the exponent, right? The inverse, though, it's not really described that well. It just says that for the inverse you have to use the opposite sign in the exponent and multiply by 1 over n. So we'll see if it's that easy. It sounds a bit way too easy, to be honest. It says that you can basically just use FFT as the inverse, so that's kind of nice. Okay, and finally we want to do like x out at index k plus equals, right? So we have a sum, and we do xm multiplied by complex exponent, and here we do minus exponent, right? So that should be it. Again, it looks kind of simple, but that's that. What I'm not sure if, do I want to make it a header only thing? I don't know. I don't really mind. So this is gonna be the FFT like conversion. Okay, let's go ahead and let's do the IFFT. So it's gonna have the same signature, I guess, but it's gonna do the inverse. So let's go back to fft.c and let's see. So I guess, yeah, it has the same signature, right? Because we are gonna have n elements, but as per Wikipedia, we have to remove this minus sign from the exponent, and I'm pretty sure at the end of this thing we have to do x out k is x out k divided by n, right? Because it says here that you need to divide by n, so I think that's what it means. And the minus from the exponent, pretty obvious. We saw the minus here, so we just remove it, I guess. So that's kind of it. So let's see if we can actually use this thing in our code. Okay, so first of all, let's go into stack.h and let's take a look at hide LSB. So we are gonna say hide FFT. So we are gonna try to hide using FFT, right? A payload inside of the bytes. And the compression is not gonna be needed for now at least. And then we have show FFT. So I think, yeah, we are gonna send the bytes. We're gonna have the bytes length, we're gonna have a uint payload and a payload length. All right, so initially let's try to implement these things by just calling to FFT. So they're not gonna really hide anything, but I want to see if the image is gonna look the same. Right, so let's include fft.h in here. I have to change the make file, so let's also compile fft.o from fft.c and fft.h. This one also requires lm, but we already have. I don't think it requires like L complex or something. Okay, and stack.o now depends on FFT. I mean, it also depends on ace.h, which I mean, you can, you know, the name of the library, you can think of it as like helping, right? Aiding, some help. It's not a disease. I mean, sorry about the naming convention, but yeah, I mean, it was kind of funny. But let's go to stack.c. So we have this F15 here that we can use here. Okay, so I guess the first step would be to convert the bytes into complex double pointers. So we can do something like complex. I guess for complex we need complex.c. So we have complex double pointer. I guess I'm gonna call it x just because. And this thing is gonna be equal to, we need to allocate some memory. So let's do ds aids realloc. This one takes, you know, the old pointer, so null, and then the size. I guess the size is gonna be bytes length multiplied with size of complex double. I don't know if complex double is different or not, but yeah, whatever. Then if x is equal to null, I don't even know, like if allocation fails, you should probably just exit, but you know, let's do stag result is equal to stag okay. Here I'm just gonna do return defer stag error and return result. I mean, we could do something like stag failure reason, failed to allocate memory. I mean, it's pretty fine. We can actually do aids failure reason. It's like, okay, just propagate the error message. Yeah, fair enough. Okay, so the next step would be to convert from bytes. So right now the bytes are numbers between 0 and 255. right? And what I would do, honestly, is make them between 0 and 1, and then put them inside of this x double, right? So let's do a for loop for size t. I is equal to 0, I is gonna be less than bytes length I plus plus. I guess I'm gonna do x at index I is equal to, right, we kind of know that these are gonna be just double, so let's convert bytes at I into double, and let's divide by 255, and we might just do plus 0 times I, something just to make it more obvious. So this is the real part of the number, and imaginary is 0, so we have this x, and we divided it by 255. So I guess now we can do FFT simple. I'm also curious how slow the algorithm is, right? So this is going to be bytes length, and for the out, let's say we're going to have an x out that we need to allocate, and probably mem set to 0. So we do mem set x out. It takes the character, so probably 0.0, and then bytes length, size of complex double. Right. So it just sets it to 0, right? Everything. Not that it matters, but yeah, whatever. So then we call to FFT simple. We should get back an x out. Then here, let's do implement encoding, and then we have to do IFFT simple. And now this one is interesting. We no longer need x, so we can actually free it. But why free it when we can just reuse it as the output for IFFT? So let's say we mem set it to 0, and then we just use it as the output. So here we pass bytes length, and we just reset it, right? And then we have to do something like this. We iterate this thing, and then we need to convert it back to bytes. So this one is going to be interesting. I would expect the imaginary part to be 0, but who knows, maybe it's not going to be 0, but hopefully it is. So let's do serial killer. Oh, just that was. And we multiply this thing by 255, and let's also math.floor. Oh, just floor. I was programming in Python. Okay, so here it's gonna say we need to include math.h. Right, like it returns a double, but it looks like it doesn't matter, so that's interesting. Okay, and at this point, yeah, sure, we can actually just say if x is not null, we free it. So A is free. All right, we remove the aids from the code, basically, if they are not null. So this should take care of memory allocations. But yeah, we'll have to implement encoding. So I'm curious if this thing will work. So let's say in our honestly, I'm thinking, let me just do that. So we have a command for hide, command for show. Should we add new commands? So these commands are for LSB, right? Now the question is, should we add different commands for FFT, or I mean, I don't know why put usage there. Honestly, I would like usage to be right above main, but whatever. So I don't know if I should make functions like stag hide, stag show for LSB, and then functions for FFT separately. Like the only reason I say that is because of this compression level. Maybe I want to do them separately, I guess. Or I don't know. Let's keep them the same. So maybe I also want a flag or something to indicate which thing to use, but I really don't like that. But then we would just write a bunch of code again. So yeah, let's just comment out the LSB part, and let's try to use so instead of hide LSB, we can just let's comment it out first, and for now let's just say hide FFT. So the thing is going to be kind of similar. It doesn't have compression yet. I don't know if you can actually compress. Maybe we can, I don't know, we'll see. But let's try to run make. Doesn't like that it's not stag hide FFT, it's wait, what? Undefined reference FFT simple. Didn't I called it FFT simple, and it's weird. FFT simple and IFFT simple. And we have the include here. Did I make a typo in this thing? Whatever, it's not that important. So let's check fft.c. This one, I mean, it's implemented, it should work. Maybe it's the make file. Maybe I need to make clean first and then make. Nope. Wait, I forgot to add the fft.o in here. Right. Okay, so now it was fine. So let's try to hide. So it shouldn't matter the compression here. So what I can see right from the beginning is that it's very slow. let's kill it. Let's try to use. Also, it was really slow just on the image. That's interesting. So maybe we need to implement the nlogn version right from the beginning. Now I'm curious if we can just printf the k value here. I'm just curious how slow it is, to be honest. Okay, let's include stdio. So curious how slow it is. So it is pretty slow. It should be 512. Wait, no, it's actually 512 multiplied by 512. Like that's our n value. Damn, that's pretty huge, to be honest. Right? And not even that. It's actually 512 by 512 by 3. So it's actually really huge. Yeah, maybe we have to implement the optimized version from the beginning. So I think that's called the Cooley-Tukey FFT algorithm. Okay, thank you. So yeah, I guess we should implement this one from the beginning. I was just wanted to see if it's possible to just test the results for this one. I tested it before, but with really small numbers. But wait, actually, what we might be able to do, just to see how it looks like. So let's. What we can do is going to test into fft.c. So this one doesn't really depend on anything. We can create a main file here, a main function. I guess we can just do an example.c just so we don't include fft.h. Let's also take a look at main. Let's get the AIDS implementation, because I want to read a file. So the file that we are going to test is going to be the one for the payload. So here we do stbi load. And let's just show. I need this part. So here we are gonna read the test.bin file into a slice. Let's just do exit. Okay, so in test.bin I'm just gonna put some data like hello world. Right, so that's gonna be it. We can just printf it to be sure that it's hello world. Should be good enough even if we don't have /0 at the end, but just want to make sure that. So we can do fft example.c into example, and we also need lm. Alright, so it shows us the right stuff. Okay, and then inside of stack.h, I guess stack.c, we have all of this stuff that we can just copy paste for testing purposes. So let's let's not even worry about those things. So size t bytes length is gonna be payload slice.len, and uint 8t is bytes is gonna be payload.str, and obviously it's like pointers. What? It wants stdint. Right, we are not checking that. That doesn't really matter. Here we need to include math. Right, and so here we are printing the slice. Let's try to print x out. So for size ti bytes length plus we can print fftx is equal to actually I don't know how to printf complex numbers. Printf complex. I can just do something like this. Okay, so just printf it as a normal float, but we just put x out I and x out I. That should be good enough. And then at the end we do kind of the same, but on x. And then obviously the cool part would be to do a printf on the bytes, and the bytes looking exactly the same as in the beginning. So that would be ideal. Ooh, it's kind of close. Helknvnold. But you know, it's wait, why is it printing K? I guess inside of F50 I'm still printfing K. Right, so we get like the transform, then the inverse transform. The string looks kind of similar, but the point is not that the string is gonna be exactly the same, because it's kind of, I guess, impossible with floating point numbers. But if you think about it as the bytes of an image, then it's gonna be hopefully kind of similar to the original image. So that's the hopes. But yeah, we saw that it's really slow, so we might want to try, and instead of FFT simple, just implement the optimized one. Let me just make sure that the original x is the same as the output x. So this is the original x, 0.28. See, it's like quite similar, 0.28. Maybe I can just zoom out so I can see, but hopefully, I mean, it's not going to be visible for you, but I mean, yeah, you know, they're kind of the same, so that's good enough. But you can see that if we try to interpret it as a string, it's kind of a bit too far. But anyway, it doesn't matter. Okay, so let's try to look into this one. And honestly, I was hoping the oven squared one would work, because look at this shit. I mean, come on, like This is a lot of math, but also what I found was that on Wikipedia we also have the pseudocode. So hopefully this one is easier to copy paste into C. Now this one, what I kind of don't like about it is that it's recursive. So it's like when you have a recursive algorithm, if you have a big, like a way too big n, an n value that's way too big, it's gonna stack overflow, right? So it's kind of constrained like that. I think there's also an iterative version, but honestly, when we are given the easy path, we should follow the easy path. So let's implement this one first. So let's go to fft.h, and I mean, I'm just gonna scrap fft simple, I guess, at some point, but let's do dit. So I think dit stands for, I don't know what it stands for, but yeah, I have no idea, but we are just gonna go with it. So it's fft dit and inverse fft dit. The signature is gonna be the same, right? And the reason why we are gonna implement some helpers in the C file. So we have these two, right? fft dit, and then let's say we have something like static void fft dit helper, and this one is going to take the x. So x is, I would hope x is the input, n is the count. I'm not sure what s is, but it looks like s. What the fuck is s doing? It's just 2s. So if n is equal to 1, then whatever, x is equal to 0. Then the first half is this, and the second half is this. Then we iterate the first half, we compute some p value, some q value, then xk, so this one gives you the dft of x0 xs, n is an integer power of 2, and this is equal to 1 is the stride of the input array. X plus s, but I don't see anywhere x. Oh, x plus s. Okay, that's what that's what s is used for. So s is the stride, so x plus s is the array starting with xs. Honestly, no idea what the fuck this is. So x plus s. So in the end, we want to call x, n, and 1, x plus s. Dft of this thing and dft of this thing. Combine dfts of two halves. Interesting. Let's just pretend that we get what the point of that is, and hopefully it's gonna work. That's all I can say about this thing. Okay, so in the end here we just want to return, or I guess we don't even return anything. It's fft dit helper x, and here it says to call it with 1 and x out. So that's, I think, what we have to do. Then obviously if n is equal to 1, this is the easy part. We just set x out 0 is equal to x0. But then it's the shitty part. So we get half by just calling this thing on this. Okay, so let's take this guy, and let's say we pass x as it is, and from what I can see here, it's just going from 0 to half minus 1. So if we just divide n by 2, if we just divide it by 2, and here we put 2 times s, it's just going to modify the first half of this pointer, so we shouldn't really worry about it, right? But then here, I guess it's just x plus s. Like I don't know, maybe it is just x plus s. We also do n divided by 2, 2 times s, and then x out plus n divided by 2. So we go to the half of this array, and then this one just starts a bit shifted somehow, because here it says that s is the stride. I mean, from what I know, the stride is just what you iterate with, right? But the thing is, I don't really see any iteration. But at some point n is gonna be equal to 1, so we are gonna do this thing. I mean, I just hope that it's x starting with s. We'll see if it's gonna work or not. Size decay. So we need to go to n divided by 2, k plus plus. I guess we don't need -1 because I think pseudocode stuff, it's like inclusive, so we might not need it. So we get p as, so complex double p is x out at k. Q is just the exponent calculation, right? It looks just like the exponent from here, almost. So here we have I times 2 times m pi times k and divided by n. So we don't have the m term. So this is just q. Well, I guess it's the exponent, and then we can compute q. And q is x out k plus n divided by 2 multiply with cexp of minus exponent, and then xk is just the addition, So k is p plus q, and we also have k plus n divided by 2 is p minus q. Interesting. Very interesting. So this is FFT dit. Let's take a look at, let's not do anything with this one. Let's look at example.c, and here let's use FFT dit. Here we don't really care about that result yet. So if we clang this thing, if we run the example, we get some results back. I should have compared them with the results from before, but whatever. I guess for the inverse we want to do something similar, but let's see. Let's say that we try the same logic, like here we just do without the minus sign. Will it work? Apparently no. So it's 235, but there was, I guess we need to divide it by something. But I get these zeros. Huh. No. Let's say let's try to use copper. Let's see if we are actually gonna be replaced by AI, because I'm curious if it's gonna be able to implement this thing without me. So I mean, probably it was implemented before, so it takes the half just like I did. It does exactly the same thing. Wait, it's exactly the same stuff. Right, it took the half, it called dit helper, it did this for loop just like I did, it did the cx stuff. Here it did it a bit differently, but whatever, I don't mind. But it's exactly the same stuff. Let's compare the results. So yeah, it's kind of the same result, right? Whatever. Let's see how it implements the inverse. Wait, it's the same shit. Huh. Chat, are we cooked? I mean, it's doesn't look too good, to be honest. Do we have an inverse? I mean, maybe it was influenced by my other implementations. So let's actually do something like this. So there's nothing it can base its implementation on. It's still the same thing, right? Even maybe the problem is that we reuse the array and it gets modified in the first one, and then in the second one it has to be the same array. I think that's the problem. But wait a second, we didn't even do that. Yeah, no, we weren't doing that, so but see, here it does something different. But I guess that's because it's being really dumb. So yeah, let's remove this one. Let's remove that one and that. So let's see now what it does. Yeah, I mean it gets to the same result. Yeah, whatever, and must be a power of 2. That's not really that important. Yeah, like it does the same stuff. So let's see the inverse. It's funny that it tries to use the dit helper for the inverse. Oh, maybe I missed this division by n. Maybe that's what I missed. But I mean the numbers looked really wrong, to be honest. And like they don't look the same. Was this 2i? Like really unsure what this one. Let's try to remove the minus at least. Wait, was this 20? Am I printing something in example.c? I'm printing the bytes for some reason. Yeah. So it's way too different. Yeah, I'm trying to build the FFT algorithm in C because we want to encode some information in images. So yeah, that's what I'm trying to do here. But apparently, I'm not sure the pseudocode that I found on Wikipedia, it's not really working for us. So FFT implementation in Python. Let's search for the Python implementation. Okay, so we have some FFT here. So if n is 1, we just return x. That's we know that. Here it takes x even, x odd, then it builds some kind of factor, then it concatenates man, sometimes I'm like, I know that Python sucks, but come on. I mean, this one is not even the right implementation because it's still n squared, right? It's computing the factor. I guess it's calling FFT like that, but okay, so fine. Maybe it is n log n. Pi times I divided by n. So the factor is just what we are computing as these exponents. Right. I don't really like that you have to allocate the memory in C because that's gonna make it slower, but whatever. X even plus factor times x odd and then times x. And there's maybe that's gonna work. We can try it because honestly I'm not sure which one we can do. Oh my god. I mean, this one's kind of oof. Maybe it's some homework or something. Maybe this one could work. Now let's copy paste it in here. So it's doing, okay, I get what it's doing. Let's remove that part. Let's put a comment with the Python code and let's make Copilot do it. So it's doing the n is equal to 1 case, right? It's splitting these two, which fine. We allocate some memory, but it shouldn't be a problem because we free it later. Now the problem is we free it after we recursively call, so that's gonna suck, but whatever. Here we compute some even odd stuff, but see here when it combines the results it doesn't do the same thing as here. Factor times x odd. It does. Okay, and what about IFFT dit? What's your opinion? So it's also normalizing, and here it's not doing the minus. Will this one work? Let's see. Copy pasted and helped by Copilot. Ah shit, it's not. Although I'm curious if at least is the result similar to what we get with a simple FFT. Let's just do it like that. So with this one we get something like 4. No, it's not even close. Okay, I mean, because with this optimized one is 2.8, like very different. Maybe we can steal it from Python. Or our last option, obviously, is to resort to, ChatGPT, and we can ask it something like, please implement FFT implement FFT function in C, and then we can give it some C code. I mean, is it gonna work? Honestly, I don't think it will, to be honest. It's looking like, I mean, even if it does. Okay, so let's take a look at what is different. So the n part is the same. It's allocating some even odd, computes even and odd. 2 times I plus 1, allocates FFT even and FFT odd, calls that recursively. Twiddle? The fuck is a twiddle? Does that x out plus half. Well, I mean, the results look different again than what we had before, but in my opinion they look a bit better because we don't have zeros anywhere. Maybe ChatGPT is onto something. How about inverse? Yeah, no, we don't really care about supporting non-powers of 2 because the image is 512 by 512, so it's not going to be an issue. Interesting. Final normalization at the top level. But why n is equal to 2? You can create a helper function, but the header contains IFFT bit. I mean, just wasting fucking trees, bro. Let's not waste trees on. I mean, we already did, but that's fine. So, okay, let's say. I mean, maybe ChatGPT is going to replace us. I mean, I'd say I was pretty close, but yeah, maybe it was just the fact that we need to allocate memory, so. But what I don't really like about allocating this memory is that it gets allocated, then we go recursively and we allocate again and again. And then sure, we free the memory, but we free it at the end of the execution, so it's kind of pointless. Okay, let's copy paste. Jesus. Let's copy paste the code from ChatGPT. Honestly, I like to do it like this, like the library name. I mean, it's not IFFT, but it's kind of the library name, and then two underscores for private, just like in Python. So this one, you can see that for cexp it removed the minus. That's the only difference. And then here it divided by n. So yeah, it was kind of copy pasted from ChatGPT, but we were pretty close. Not sure, but first let's make sure that it works, honestly. It doesn't. Is it close enough at least? Nope. But you know why? Because n is not power of 2, so we have to make sure that if n, how do you make power of 2? I did that in stack.c. I did that check. Come on, I did it somewhere. Oh, yeah, this one. So if you think about it, let's stop code because it's annoying. If you think about it, a number in binary is going to be something like this, right? So it's going to be a bunch of zeros, a bunch of ones. If you have only one 1 in the entire number, that's going to be a power of 2. So if you subtract 1 from one of your numbers and end it with itself, it's only going to be 0 if it's a power of 2, because it's going to change this thing, right? So this would become 1 0 like this. So if you end it with itself, it's going to be 0. So that's kind of how you check if a number is a power of 2. It's kind of cool. So if this thing is equal to 0, well, I guess if it's not 0, we can just exit 1 for now, because we don't know how to do IFFT on shit. Sure, like whatever, I'm gonna clean this up. It's like ChatGPT is doing a mess, but so see, it's like it's not a power of 1 or of 2, so maybe that's why it doesn't work. So maybe we had it right from the beginning, but I forgot about this fact. Okay, let's check the bin file. So test bin 1 2 3. Okay, let's do something like this. So we have a string of 8 characters, and now it's 8 characters because it's gonna have a new line. That's annoying. Okay, so now it's closer. All right, so maybe we were right from the beginning, but we actually were unlucky, and I forgot about this shitty thing about FFT. I mean, sure, ChatGPT says here that it can make it work, but you know, we don't care about it. Let's try to go back to when we had our implementation. Man, I don't even remember where. I think this was, yeah, this was the implementation, right? So if we run this thing, okay, no, it doesn't work. So the ChatGPT version is actually, so yeah, maybe the allocations fixed it. Okay, let's try to DD some data in this thing, but what I have to do is to remove some printfs because it's gonna take a while. Maybe some printfs would be nice, but oh, okay, so I mean it makes sense. It's not powers of 2, but okay, so see, it's the fuck this fast. I mean, I'm surprised it's this fast. Almost as fast as me when it's the most. I'm just kidding. Okay. Okay, I mean, at least we got the 50. Oh, something's wrong. Okay, but it's still 512 by 512s. Oh, and we also have 3 there. This is not a power of 2. I don't know what the fuck I did there. Okay. Yeah, this is not a power of 2. So what can we do about the image? Well, let's say we load it maybe with 4 channels. So what I'm gonna do is copy paste this thing here. So instead of reading that payload, let's do stbi load, obviously. Like this. Here we can just exit, doesn't matter. The image path is lena.png, right? But the problem is gonna be that is not gonna be this kind of right. So if we run it like this, it's gonna say that well, it's not a power of 2. Can we force it to load 4 channels? Nope. Printf width, height, and then the number of channels. Width, height, no channels. It's only 3. Okay, do we have some helper in stb load? Something about channels? stbi like convert or something? to RGBA. Do you know if STB image convert RGB to RGB, this thing works? No mention of STB image. Maybe it has some to force. I mean, I tried 4. Ah, okay, so I can still force 4, but number of channels is gonna be 3. So here I can say 4 instead, and it should work. Nice. Okay, so we can just put here a 4 and it's gonna be fine. Can we also just write the image to make sure that it's fine? Write PNG. So I'm just gonna write the PNG here. Let's say Lena fft.png. With height, number of channels is gonna be 4. Width times 4. So let's try this one. Cafe Lena. Okay, that's interesting. So as I said, like for text, it sure looks a bunch like a lot different, but for the image, I mean, it looks the same. I don't see. No, hopefully it actually works. That's quite nice. Okay, that's some good stuff we got here. So in FFTC, yeah, I'll have to clean this up a bit because I don't know, ChatGPT doesn't. I mean, it is what it is, but sometimes you have to use ChatGPT. Okay, so let's get back to using hide, like implementing hide FFT. So here we were trying to do this stuff. Well, actually, what I'm gonna do is steal this thing. Right, and let's put it here. So if bytes length is not a power of 2, then we just return defer stag error, and we set the failure reason to something like the input data is not a power of 2 shape or something. I mean, we don't want it to be power of 2, but power of 2 like like in shape. Okay, let me just declare these things in the beginning, because otherwise we are gonna have some complaints from the compiler, some warnings. But yeah, so here we validate that we have a power of 2 size, then we allocate x, we do the byte stuff, divide by 255. Here we lose some precision, that's kind of the idea. Then we do FFT dit, which is gonna be faster, allegedly. Then we do the inverse dit, and doing FFT and inverse FFT we also lose some precision, obviously, and then we again lose some precision when we multiply with 255. So that's kind of where we are at. So let's go to main, and since here we are using hide FFT, let's change this to 4 for now. So here we are gonna put a 4, we are just hard coding things, and here we are gonna put a 4. Can I put num channels here though? I don't know, I'm just gonna put 4 for now. I'm gonna play around and see if I can put num channels here, and here increase the stride, but let's leave it like this for now. So let's do make. Sure, some unused parameters, doesn't matter. Just to make sure, 115. So yeah, we are not using payload, right? We are not using payload length, and then for show FFT we are not implementing the function yet, so it doesn't matter. So let's try to hide this stuff. Message successfully hidden. I mean, we haven't hidden anything yet because, right? So we get that. That's cool. So we want to implement some kind of encoding at this point. So here I was checking if we actually fit. So let's also add this check somewhere at the top. So here we want to make sure that the payload length, maybe we also want to straight up add size of t for the size, is greater than the bytes length. So I guess if it's greater than bytes length, we fail. Data is too big. Okay. But now let's try to implement some kind of encoding. So let's do a for loop. Size ti is equal to 0. Let me check if... yo. Man, you had so many comments. I'm sorry for not reading them. Yeah, I50 is the fast Fourier transform. Yeah, so I'm trying to implement basically taking an image, we convert it to its frequencies using FFT, and then we are gonna encode in this FFT some payload, right? And in the last stream we did the same idea, but we used least significant bit encoding. So instead of, you know, we wanted to have some kind of benchmark. So the least significant bit is basically the baseline, where we are trying to hide in the LSB of each pixel some data. And now, yeah, we are trying to improve that algorithm by using FFT. And the idea is, can we hide more data with FFT, or is it like which one is gonna be better, right? So that's yeah, thank you though. So yeah, okay, let's continue. So we have this I is less than payload length, I plus plus. Right. So we have the bytes. So what I would say we can do here is take one of the bytes. So one side, I mean, yeah, uint 8t. Do I use uint 8t? Yeah. So we can take one of the bytes from the payload, and here the idea is we need to encode somehow have to encode. I mean, are we gonna do bits again? Kind of. Or maybe first let's test my my hypothesis. So I would say that if we do here bytes length and we do something like so x out at this point is our frequencies, and we do something like x out is floor of serial x out at I, so this would be I plus C imag x out I. Right, so I'd say what would happen if we set, like I want to use the fraction part of the real term as the encoding. So what would happen if we do this? Will the image look like shit? Actually no, actually it still looks fine. So yeah, what I want to do here is to basically do something like 0.5 if we have a 1 bit and 0 if we don't have a 1 bit. So interestingly enough, I think, but how can we put multiple terms such that we don't lose any information? Can we do something like that? So if I do here, let's say plus 0.5, then it looks the same. If I do plus 1, oh, I'm not compiling the right thing. Or no, I was. Oh, so now it looks like trash, okay. But here it was looking fine. Right. Nope. Do we need some kind of offsets? Like at what point it becomes ugly? That's curious. Oh, it has some transparency. Okay, let's say we don't do any of this. So now it looks fine. Hmm. Let's just try to print f some values and take a look at them. So x out at index I. Wait, it wants ah, serial for snake and then build. So quite a few numbers. Let's try to do something like plus 0, 1. See how much it influences the... what? Is it really that... Oh, so it... Ah, it's because C imag, it needs to be multiplied with I. I'm stupid. So I have to do times I. Yeah. I don't know why I was thinking that... okay. So maybe flooring this thing won't affect the image as much. Let's see. So if we yeah, it doesn't affect it. So that's cool. Okay, perfect. So this means that we can actually hide some stuff in this value, because right now it's basically 0 after the dot. So yeah. Okay, so that's nice. What can we do next? So I'm thinking just that to hide some information, I would do, if a bit is 1, as I said, I would do a number that's greater than 0.5. But that means that we can only hide 1 bit in a byte. So that somehow is worse than what we did for the LSB. Right, that would be kind of not ideal. But I don't think we have a better option at this point. Unless we also use the imaginary number for that, but no. Let's just use the real one. Fine, let's try to actually do it like that. I'm gonna think of a better way. Maybe there is a better way, but for now, let's try to do it like this. So, in fact, I mean, at least it's gonna be easier than what the pain that we went through last time. So, I think at least, hopefully. So let's see. So I would like some kind of util function. Do I want this util function? Yeah, like here I still have to do byte size multiplication like this. And like that. So I need to find those two for loops from hide LSB. So something like this. So something like this here. So we would have a for loop over size t. We get a payload length. Then I don't really want to use a helper function this time. Let's just say that we have x out at index I is the floor, plus this part, and I mean, kind of makes sense maybe to have a helper, but let's just hard code it for now in here. So we do this kind of for loop like yesterday, then we get we don't really need that. We don't need this thing. We are not gonna use a mask. We don't need that as well. We don't need it. So here's gonna be byte size. Okay, so here we can use j so that we don't use I again. So it's minus j minus 1. The byte is length byte. Okay, and then we have to do something like plus j, right? I plus j. Wait. So I is gonna be from 0 to the number of bytes in our item. This one we get it, and here I think we have to multiply with byte size, the I. Or am I wrong? No, it's fine, like that. Okay, so here we have this value, kind of a bit long, but double, let's have something like double flag, and if bit is equal to 0, then we have 0.0 obviously, otherwise 0.6, let's say, or 0.75. I guess 0.5, and we are gonna compare with 0.25 or something. So that's that, and here we also add the flag, right? Okay, and here we are doing kind of the same stuff. From I is equal to 0, here we are gonna take the actual byte. Whatever. So we are taking the actual byte. Byte from the payload. We don't have to do any conversions because it's already that, so we just take the byte. Then we need this j stuff. We need to take the bit, and here we need to add the header size, so this kind of offset. I mean, I'm gonna clean this up, but for now I think it's fine. So this should maybe hide the information. But I'm pretty sure that at this point that information is way too big. So let's make it a bit smaller, like maybe 64 or something bits of information. And then if we run this thing, it should be hidden. The image should look exactly the same. So maybe that's the advantage of using FFT, that maybe the image looks more similar. couldn't tell, but yeah, so I guess that's the idea here. So let's try to do the other function, the decoding function now. So for decoding, we still want to transform the bytes into FFT, right? But this time I think this one needs to be a pointer. Stack H. Right, and here I called it message, and it's double pointer, and here it's message length. Okay. So we don't have this check. We don't know it yet. So we need to check how we did the show LSB. So we did some util here, and the util is basically just the okay. So we might be able to do that. Let's see. So here we have that. Length byte. And the decoding function would be kind of useful. Yeah, maybe I want to implement these helper functions. Let me do them here. So stack util show FFT is gonna take in, but it's not really a pointer to char, it's complex double pointer. Then we have a single byte, and we don't have count because we don't do that yet. So we iterate until bytes, then we don't have that. We have pointer byte here. We care about the flag mostly, so let's say flag. I mean, flag is just okay. Let's do int bit is serial pointer greater than 0.25. I said pointer at I, right, if it's greater than 25, and that's basically the bit, right? I guess we want to end it with this amount, just to make sure. So maybe it's just unsigned char then. So that's gonna give us the bit, and we can just shift that bit like that. So maybe that's what we want to do with our util show, and maybe we want to implement a util for the other one as well. So this is the show FFT. Here I want to do stag show util show. We send PTR. I guess here for the PTR we were sending, let me just double check, show LSB. we were doing. No, this is hide. I want to show. Show. So for show, I was doing something like pointer. So here you have to be kind of careful that, well, I guess if you do I times byte size, should be fine. But obviously pointer is X out. And then here we want to write into unsigned char pointer message length plus I. Right. So that's gonna give us that. The unsigned char pointer. And then we can do this check right here. So if the message length times byte size plus that is too big, data is too big. I mean, this doesn't really matter, but it's just checking. And then we have to do the other part, which is allocating the memory and that. So this is gonna be allocating the memory. I'm sure what it doesn't like here. It's the fact that it's const for some reason. Stage. Yeah, I don't know why it's const. Whatever. So here we were allocating the message. Then we need to do the similar thing to this. So X out byte size. We need to add this extra byte size, and then we need to send star message plus I. I think this should be good enough. And then we are just calling that. Now why the compiler is slow. Okay, so let's check out names. I wanted to make sure that we don't have any problems there. So in stack show, I think we want to load the image with 4 channels just for you know, the purpose of this. And instead of show LSB, we want to show FFT. That would be kind of cool if it works. Then if message length, blah blah. Okay, so this part is fine. So yeah, I think maybe a flag for switching between LSB and FFT. I don't know. I'll decide on that later. It's not important. So we do that, and let's try to show Lena out. So data is too big. Yikes. Did I make some mistake here? Let's print F the message length. Obviously dereference it and that. So hiding works fine. And then if we show, okay, so probably something wrong in here, I would guess. So we did size of T. Makes sense? So it's like 64 bits of information here. No, all of this is good. Okay, let's actually implement the hide helper, because util hide FFT. So the hide utility, if I'm just gonna copy paste this one for reference as well, we basically want to do this kind of for loop over the byte size, then sure, I was just taking the bit, then masking, we don't need any masking, we don't need that part. Here I was just computing the bit, just like I am computing the bit here. But that's not right, I have to use the byte for that. Wait. Let's copy paste this part as well for reference. So this is the second reference that we have. So we're doing this this for loop, then the bit, sure, it makes sense to have something like percentage. Wait, but why do I send it should be just byte. It should be just byte. So we have the bit, let's do eyes, we have the bit, then we have the flag 0.5 and 0, and then we want to write something like ptr at I is equal to floor serial ptr at I plus cmag ptr at I times capital I plus flag. I think that's but here is no longer const. I think that's what we need to do, kind of. What I'm missing is the fact that we need to, no, it's fine. So we take the byte, convert it into a bit. If it's that, we do that. ptri is floor serial. I mean, it looks fine to me, I guess. And then this one was used like this. So here I did, or I should do, x out plus I times byte size, length byte, and that's it. It's kind of the same stuff, honestly. Again, here we just need to make sure that we append this extra stuff, and then we put the byte, as in payload at I. It's the same thing. Okay, time for some printfing. Printf percentage d I can just show it like this. $128. I mean, that's fine. Because it is 128. Right. And then in hide FFT, we take the bit and we put 0.5. So if I do printf %f flag, I would expect to see a 0.5 once at some point. Oh, what? It's also from the, yeah, it's also from the other one. Shit. Yeah, whatever. But this one should write 0.5 in the thing. Size tj is k, I guess, if I type k. Byte size, k is less, k plus plus. Let me just print f serial x out at I times byte size plus k. Like here I would expect to see a 0.5. Right, all of them are 0 except this 0.5 from here, which makes sense because it's the last bit from 128. 1, 2, 3, 4, 5, 6, 7, 8. But the rest of them are 0. So that's what I expected to see. Now, if we go to decode and we take a look at X out here, is it also gonna be 0.5? It's kind of a bunch of numbers. Maybe we want to use different numbers here. What if we use 0.25 and here 0.2? Like make them smaller, I don't know. It's still huge. So here we are making it 0.25 or something. So for show FFT, we do that, convert that. Oh, I'm still doing a FFT dit. No, it's fine. I have to do FFT dit. So yeah, that's kind of interesting that we don't get the same values back. Let me just try to do the same thing immediately after we encode it. So here we just memset x out to 0, we FFT it, then we do that, but we don't show that, but we just show the bytes and we also show the values. I'm curious why it changes so much. Oh, it's kind of the same. Here it's 0.75 though. Interesting. Is it because I'm doing this here? Hmm. Whoops, I don't know. But wait a second. It said 0.75. I'm just... Yeah, I guess it changes quite a lot, but... C-abs. I mean, I can try to do C-abs, but that's... I don't think that... well... See how the data, it's like not that changed right here. But if I try and do it after we compute the bytes, how is that gonna look like? So what if we are doing it here? Damn. So that's the main reason. Do we need some kind of offset? Maybe certain intervals are not working. Let's try with 100 or something. So I would say here we can add some offset like that. All right, in our thingy. So here when we print, we also need to add the offset. The offset still doesn't really help. But what about if I used C-abs? Also was kind of off. I mean, it changes too much, to be fair. Okay, let's try to put this one really low, like 0.1, and then make, I don't know, this one 0.2 or something. Yeah, it's still changing. What? Oh, no, it's fine, it's fine. I was thinking that, oh, I used X instead of X out, but no, it's X out. Yeah, I'm not really sure why this happens, honestly. Like we have this length we encode. I mean, the encoding itself looks fine immediately after, and even if we inverse it here, the problem is that if we multiply with 255, it's not necessary that this thing is between 0 and 1. That's a good point. So let's memset here X out, and then we compute X out first, like this. We can, oh, and I'm also floating it. Let's do just C abs. Then we also have a double max value or something. If X out I is greater or equal than max value, I guess max value is just X out I. What? Yeah, fair enough. Let's just allocate new memory. Let's make this one double values, and let's allocate for now. It's fine. We are just checking if it works, right? Okay, so here I'm gonna do values, like that, max value. Then we need another 4, and I'm gonna say values I is divided by max value. So now it's normalized between 0 and 1. And here I'm gonna do values at I times 255. Is this gonna work? Still no. I'm curious though if I mean, somehow the image looks the same. It's pretty cool. What if I do plus 100? Like, I don't know. I'm just curious. Is the image, I don't know, I have to make. Okay, so at least we know that this thing kind of works. Yeah, honestly, I don't know. I might have to do some research about this. Like, how can we actually hide that information? Because I wasn't expecting this to not work. Yeah, I know, famous last words, but just a 50. Yeah, like this part, I'm not sure why it's so different than what we get here. So that's the part that kind of sucks, because we can do the hiding, like it kind of makes sense to do it like this, I don't know, I wouldn't change those bytes too much. I think it's fine to have something like this. But then the show part, like the interpreting the data, it's kind of off. Right, because of this kind of conversion, I would assume. And what if I put 0.9 and then if it's greater than 0.9, or actually greater or equal? Maybe it's one of these still doesn't work. Yeah. Okay, so I was testing what, like putting 0.9. Yeah, I don't know, maybe I'll just try to look into this why it's not working, but and I'll come with an update, but for now I guess it's I mean, see, now the numbers are looking a bit better, but we still have numbers that are greater than 0.9, so that's kind of the problem. So yeah, I mean, I'll try to check on my own why this thing doesn't work. Not really, I don't really have an idea right now, so yeah, don't want to waste too much time on this one. Might have to look a bit into how other people do this one. So yeah, hopefully this was kind of useful for you guys. I don't know why that sound, but yeah, like you know, we are gonna check it in the next one, and we'll also try next time the DCT. Maybe that's gonna be easier. No. And yeah, see you the next one.